What's going on, Justin, and the rest of the physics group that isn't here but should show up? Let me talk to you guys quickly about acceleration. And Justin, since you're just here, just you and me, let's chat about this thing. Now, acceleration is defined as the change in velocity divided by the delta t. And we know what the delta means, right? You're not scared of what delta is?
No, everyone that's here should have gone over it with us.
Yeah, it's just
or they should have reviewed it and seen it in the textbook.
Yeah, we're just taking a look at the final velocity minus the initial velocity. All right, now here's my question for you. Click Beetle writing itself. Writing itself. All right, let's see. A batted baseball. Let's take a look at that. That's 3. The acceleration of a batted baseball is 3 times 10 to the 4th power. So that's 30,000 meters per second squared. I have a question for you. Does that mean it's moving fast?
Relative to what? Because all speed is relative.
Okay, well, what I mean is maybe relative to the batter, right?
The batter usually isn't moving very much
Well,
unless they hit it particularly hard and it moves it back a few
let's say
centimeters.
relative to home plate. Home plate is standing still. So is this baseball moving fast relative to home plate? I'll put an acceleration with little b's.
Yes, it actually is, compared to the relatively minuscule movement of the batter itself.
All right, here, let me ask you this. How's about this? The acceleration of an elevator is equal to 3.
All right.
3 meters per second squared. Does that mean it's moving slow relative to the ground floor? You know, the ground floor doesn't move, but I mean, the acceleration of the elevator is 3. Does that mean it's moving slow?
The ratio between it and the ground moving as fast is more than that between Usain Bolt running the 100-meter dash and a Boeing 747 going halfway across the globe.
Well, here's my question, is which one's moving faster? Is this one moving faster or this one moving faster?
The baseball, but it's a different direction.
No, I mean, let's say they're moving.
It's moving in a different way.
Let's say that you hit this baseball straight up into the air, so they're moving in the same direction. Which one's moving faster?
But the baseball moves faster initially, but it slows down rather quickly due to air resistance on the stitches. The elevator doesn't have a lot of air resistance because it's in an enclosed environment, so there's very little air turbulence.
Well, see, the thing is, the point I'm trying to make is I'm tricking you, and I'm actually successfully doing it, Justin, is I'm tricking you into thinking that acceleration is the same as speed or velocity.
It's not. I know it's not.
Right. Because
I just explained to you that I knew it wasn't.
Even though this acceleration is a really big acceleration, it could, at that particular moment, be moving at 0 velocity. Is that correct?
The baseball could not be moving. Yeah, you're right. They could hit it with that force, and for whatever reason, the baseball would only move a little bit and then fall straight to the ground, in which case it would have no motion.
That's not what I mean. That's not what I mean. What I mean is this. Like, okay, so here's what baseball does. Say that the guy hits it dead on, so it hits it straight back to the pitcher. So your baseball is going this way, right? Out of velocity.
Okay.
Right? It's not slowing down. It's not speeding up.
Okay.
I guess you could say it's slowing down a little bit. But then all of a sudden it goes this way with a high velocity. This is being thrown.
That would negate its velocity, but it would not negate its speed. If it somehow expended 0 energy in the transfer, which by the way is physically impossible, then it would not change its speed.
Wait. But what
its
I'm
velocity
saying,
would change.
Justin,
Changing direction equals changing velocity.
Justin, what I'm saying here is that if the velocity is going negative in this direction and it's going positive in this direction, then at some instant in time, it had to have been going 0. Would you agree with me?
Of course. Unless of course you're trying to trick me again.
I'm not trying to trick you. I'm just saying at some instant in time, this velocity has to be 0 because that arrow has to turn around the other way. right?
And change in direction equals change in velocity. It's a
Right.
basic
So
physics
what I'm
principle.
saying is, when I asked you, is this baseball moving faster? And really, you can't tell because I could have had this elevator which is going at a very slow acceleration, 3 meters per second squared. I admit to you that's slow. But what if I had this thing accelerating at 3 meters per second squared for 10 years? You see what I mean? You'd actually be going faster.
If a baseball continued to, you're asking me over a period of 3 years if they somehow had a continuous source of movement, which one would go further? And I'm going to say the elevator.
No.
I'm going to say the elevator.
That's totally wrong. The baseball would go further, but that's not what I was asking you. What I'm asking you is which one's moving faster, and what you should say to me is, well, it depends on how long or on when exactly you're talking about. Because technically, even though this thing has a high acceleration,
everything.
it doesn't mean that it's moving fast. Even though this thing has a low acceleration, it doesn't mean that it's moving slow. It just means that its velocity is changing slow. I mean, this could be moving at 1,000 meters per second, and then the next second later, it could be moving at 1,003 meters per second. This is still moving fast. Now, granted that this thing could be moving at 0 meters per second, and then 1 second later, it's going 30,000 meters per second. This thing is moving faster. But what I'm saying here is it depends on how long the interval is going for. Does that make sense to you? So that's acceleration, because the problem that I have, and the reason why I'm going through this, what you would say seemingly dumb exercises, is the problem I have is so many students get that confused. They mix up the concept of acceleration and speed, and they think that for some reason, if you have a high acceleration, it means speed is moving slow or moving fast. And low acceleration means speed is moving slow. And that doesn't make that's not it at all.
Speed. I thought acceleration was initial velocity. Isn't that right? That's how fast it's moving initially, and it can and does change. It will change whenever it changes speed, and it will change whenever it changes direction.
No, your acceleration.
Because a little tiny bit of energy is expended in changing direction.
Your acceleration is how fast the velocity is changing. Now, in physics, we will only give you problems where if I have a velocity time graph, where we have constant accelerations, at least in this physics. You're only going to have problems that have constant accelerations. So your acceleration is actually like, think of it as the change in velocity over time, which is the slope, really, of the velocity time graph. This, because you always have, I just told you that you always have lines. You'll never see a velocity time graph that looks like this. Does that make sense? You'll see a position time graph that might look like that.
Of course. Can you, Mr. Dalday, can you please explain to me, or rather to everyone else in the class that might not understand, why they'll never see a velocity over time graph that is a curved function?
Well, and that's
why will you never see that?
Well, that's because it doesn't occur in nature. And the equations that I showed you, and I'll show them to you again, but remember those 4 equations I showed you on Friday? They only work.
Yeah.
They only work for constant acceleration. So
did I technically already learn the equations?
Yeah, you learned them on Friday.
The basis of the equations for calculating velocities that move in a curve when I learned about how to calculate parabolas and functions involving the use of x to the third power.
To be honest with you, if you ever have a velocity, see, the reason why I won't teach you velocity time graph that looks like that is because in order to do that, it would require a solid background in calculus. And so you haven't learned calculus yet, so therefore I can't really teach you this yet.
Okay.
So that's why you'll never see it. Okay. And it's not to say that it's impossible to solve. It's actually not that hard to solve at all. But for you, let's just focus on, and what I'm saying is for first year physics students, even for first and second year physics students, we pretty much only consider constant accelerations. And a constant acceleration could just be a negative, it could be a constant negative acceleration. to be a constant positive. This is a constant positive. What I mean by is we're only going to see velocity time graphs that are in lines, that are straight lines. Okay? So this graph that they have here with acceleration time graph, and then they have this slope or this curvy looking thing. That's a problem that you probably will never see because it's curved, and then that would require calculus. So it'd be unfair. All right, let's see.
Oh, okay.
Here's another thing that's a little bit funky for people. Okay, so I want to make sure that you understand this. All right, if I have a car, and I'm going to make this the most simple car ever. I know. I'm just not going to take the time to draw. And it's moving at a high velocity. Let's make it big V. Okay. And then at some later time over here, I have my same car, and it's moving at a lower velocity. I'll make it a smaller V. It still stands for velocity. It's just big V, little v. Got it? Or maybe I'll do this.
All right.
VH and V low. So V high, V low. Okay? This is 10 seconds later. Alright. Which direction is the acceleration going in?
Relative to what position? Starting position? Okay.
No,
it's going...
Well,
to you it would be going to the left, and to me it would be going to the right, but...
Well, no, what I'm saying is it accelerating or is it decelerating? Maybe I should give you a little coordinate system. This is the positive x direction.
Okay.
So is it
If
going
I knew
in
how
the
much
positive
it would...
direction? Is the acceleration going in the positive direction or is it going in the negative direction?
It's actually slowing down just a little, but it's not slowing down much at all.
Well, no, I mean, I didn't
It's
tell you
actually-
exactly the numbers, but I mean, maybe if you want, I can give you numbers. This is 10 and this is 3.
Yeah, see? There's my proof right there. I didn't even know the numbers and I still knew the answer.
Well,
Because
yeah,
it was
but
that- it
because,
was
well, you
easy.
did know that this is lower than that number because this is called V high and this is V low. Even how I drew the arrows, I drew this as a long arrow and a small arrow. So you know that
Because you were trying to confuse anyone else who didn't understand how
no, I'm not
velocity
trying to
works.
confuse you at all, but what I'm trying to say here is your acceleration is actually, and when I draw acceleration, I draw a little squiggly line. Your acceleration is actually negative. You're decelerating. You're slowing the car down. So your acceleration is actually
Exactly.
in the negative direction. So here's a concept that really freaked people out. You can actually be moving in the positive direction, but be accelerating in the negative direction.
But then it makes sense that when you tell them that negative acceleration is just deceleration, which is a concept they should probably already be familiar with.
Yeah,
at that
sure,
point.
sure. Decelerating is basically acceleration in the negative direction. Yeah, all right, I'll go with
Going slow.
that. We cool with that?
Yep. I
Now,
just hope everyone else in the archive can understand.
I just told you about when we ever have a velocity time graph, we're only going to see this kind of stuff. So we have a velocity time graph, we're only going to see straight lines like this. This will be our velocity, this will be our time graph. And so I showed you where these four equations come from. Let me just write it down. V equals V naught plus AT. And that's just y equals mx plus b. That's just the concept behind that, right? We also
Okay.
have the equation x delta x equals 1/2 v naught plus v final times t. Okay? And I showed you this on Friday. Where we got this is equivalent to y equals mx plus b. That's where that comes from. This right here is
Wait, we derive? Did you have me derive that one?
yeah. I had you derive.
Did you have
all
me
of
derive
these.
that one?
I had you
Into
derive
simple
all of
equations.
these. Yeah, exactly. I'm just reminding you of that. This equation came from.
All right.
Remember, you derived this. This was really just the area of this triangle plus the area of this rectangle. That's where I got that. And then remember, I took one of these and I put it in there, and I ended up getting this equation, which is, I told you, super useful. We cool?
Yeah, I vaguely remember that. It's somewhere in my brain.
Well, instead of putting it in your brain, you don't need to memorize it. Just write it down on a piece of paper for now. And then the last one is not delta, but it's v final squared equals v initial squared plus 2a delta x. And I didn't actually prove this one to you, but I told you go home and prove it to yourself. It's not even that hard. It's the same trick we did here, but instead you're getting rid of the t. Are we cool?
Yeah, can you keep that equation on the screen for a little bit longer? I'm writing it down.
Yeah, sure. In fact, I'm just going to keep it up here the rest of the lecture, probably.
Thank you.
All right. Now, I told you that for the velocity time graph, you'll never see a curvy thing. But I said that for the position, that doesn't mean that for the position time graph, that's fair game. Because parabolas is exactly what, if something looks like this in a velocity time graph, then what it's going to look like, here's a velocity time graph, what it's going to look like in the position time graph. Okay, think about it. Its velocity is getting started at 0 and it's getting faster and faster and faster and faster. It's actually going to look like this, which is a parabola.
The motion is
So
the level of motion is increasing at a time.
These two graphs are equivalent to each other because this is graphing your velocity versus time, whereas this is graphing your position versus time. You'll have curves in this one. You'll never have curves in this one. Okay?
Okay.
And you see how this right here represents that? These are actually saying the exact same thing.
I can actually see that.
Alright, good.
Hold on, I'm trying to look at the screen a little bit closer. Don't erase that. Yep, the slope is about the same.
No, it's not. There is no such thing as slope when it comes to this.
I'm sorry, I meant whatever term would apply towards that constant.
Well, here's what it
The
is.
equation.
Think about this, alright? If we were to take a look at the slope of a tangent point on this graph, that would be the velocity.
Oh, that's what the textbook meant.
That's what the
said
velocity would be.
tangent.
So I'm going to make a tangent point to that graph. What is my slope of this keyboard right now?
That's 0.
It's 0.
It's 0.
Which is why it corresponds to this velocity being at the 0 point. And then as I put it up this way, what is my slope? Is it bigger than 0?
Oh, okay. Now you were trying to.
Look at the angle.
Okay, now is that you're still doing it relative? It's very hard to tell, but it's a small angle, so I was going to guess it's between 15 and 35 degrees.
So it's probably.
Can you get like a protractor and tell me what it says?
Well, see what I'm trying to say is here at this same exact time. If I were to put the same time, the velocity is getting bigger. It started off at 0 right here, but then over here it got bigger, and then over here did it get bigger or smaller?
It got a lot smaller, which means at one point it's just going to be a straight line.
No, it didn't get a lot smaller. It got a lot bigger. It's a lot more angled. This keyboard is much more angled.
Yeah.
Here. So
the curve is going to become a straight line at one point, isn't it?
A bigger number. No, the curve will never become a straight line. That's not the nature of a parabola. But this velocity, this slope will get bigger and bigger and bigger. So this thing will go up like this forever. And then this thing would just go straight. These graphs mean the same thing. This graph is just measuring the slope at any given point of this graph.
Give me the function for that. I want to see something. I was gonna plug the equation that you used to get that graph into Desmos, because I can zoom out a lot more in that program.
All right,
and see
I'll give it
exactly.
to you. This one would be. This one would
The
be.
fourth one.
Let's see.
What are we doing right now?
Oh, hey,
So
Catherine.
confused.
Did you just come in?
Hey,
I joined like 5 minutes ago, but I've just been watching.
And you're wondering what's going on. All right, Catherine, you weren't here on Friday, were you? Oh no, you were online, but you were having a lot of trouble, right?
On Friday,
You were
Friday the web class?
that was the lab that we did.
Oh, the lab. No, I didn't go to the lab.
Okay, but okay, so you weren't here at all.
Yeah, I wasn't able to make the lab.
All right. Uh, what I'm doing right now is I'm actually going over a pretty important concept. And actually, if you don't mind, Justin, I'm going to probably jump off of this since Catherine's here. Because she wasn't here for these equations, and I think that they're super important. Okay. Now, Catherine, what I'm going to ask you to do is, did you see the archive? You know where to find that?
Oh, I didn't know that the lab was over video. I thought it was just in person.
The lab. You know what? I think. You live on island or do you live off island?
I live on island.
Okay. So if you can make it into the labs, that would be great. I think that what I'm going to do in the future is make the labs just in person and then record a video of it and post that up to YouTube. Because it's too hard for me to run a lab and do live interaction with them at the same time. So yes, the lab is actually going to be doing that way, but for the most part, I did record this past lab. And I introduced to you these 4 equations, which are super important. And I actually went through and derived them for you. So if possible, can you go and check that out? Because I want to use today, I don't want to re-derive these equations, I'd like to use these equations. Is that alright?
Okay.
Alright, anyway.
Yeah.
Here's these 4 equations, and let me at least just tell you how to read them. You can go and check out how to derive them. They're not even that bad. But anyway, this says velocity. The V stands for velocity, and usually, I guess I should have put a VF there because that stands for final velocity. So the final velocity is equal to the initial velocity plus the acceleration times time. That's what all of those equations mean. This delta x is really just your change in position. You're talking about like instead of just your, it's the delta means change in. So your delta x is your final position minus your initial position. Are we cool with that? Can you at least read these equations without being scared of them?
Yeah.
Okay, cool. Now let's take a look at some example problems. Alright, so these are the 4 equations that they gave you. This one I didn't give you, but that's just the definition of average velocity, which kind of makes sense, right? Your average velocity is your initial velocity plus your final velocity divided by 2. That's just taking the average of something.
Mm-hmm.
Let's try this one.
Yeah.
I'm going to look up the numbers for it. It's in the textbook. I wanted to run through this problem with you guys. Kind of go about how I go about solving it. Alright, here we go. So we got this dude. I'm going to do an example problem with you, so I want you to pull out a pencil and paper. We got this dude, and he is traveling, and that's his car. I know, it's terrible. I'm sorry. I am an artist. I actually like drawing, but not when it comes to doing physics real quick. Anyway, we got this dude, park ranger, he's driving, and all of a sudden he sees a deer in the headlights. This is very related to the lab I wanted you guys to do, because I want you guys to calculate how long, or, like if you were to stop and you see a kid jump out in front of you, will you be able to avoid the kid? Let's see, the ranger who was driving at 11 meters per second. So his initial velocity is 11.4 meters per second. So I'm just writing down the information I'm reading, all right? Immediately applies the brakes with an acceleration and slows with an acceleration of 3.8 meters per second squared. So actually, is he accelerating or is he decelerating? Is he accelerating or decelerating? And Justin, you can chime in. You can talk to me through this. Catherine, if you don't know, just say I don't know.
I don't know.
All right. Think about driving and you see a kid jump out in front of you. You're going to slam on the brakes. So you're going to speed up. You're going to try to speed up, or you're going to slow down.
Speed up. Just kidding. No, that'd be horrible.
Yeah.
Try to slow down.
What kind of American are you? All right. Anyway, I would slow down. So actually, this acceleration, they told me that he's slowing with an acceleration of 3.8. I kind of got to know that Oh, you mean he's got an acceleration of negative 3.8 because he's slowing down. Does that make sense to you? Now,
Yeah, I'm gonna just reply by text though now because I need to let my puppy in. He's gonna be loud and barking.
that's fine. Turn off your mic and then reply by text. But make sure you guys reply because I like talking back and forth with you guys. All right. Now here's the other question. I have the velocity initial. I have the acceleration. There's one more piece of information that I actually know. So let me read you the rest of the question. If the deer is 20 meters away from the ranger when the brakes applies, how close does the ranger come to hitting the deer? Okay. So, what is that other piece of information? Do I know about the time that it took? Because I'm showing you guys how I go about these things. I know what you're doing, Justin, but I wanted you to work on this because this is important. I don't think you even know how to do this. All right. Look at this. This is how you solve these problems. There are 5 different variables here. There's V final, there's V initial, there's acceleration, there's time, and there's delta x. Those are 5 different equations. Okay? When you're given these physics problems, you're going to know 3 of them. You're going to be asked to look for one of them, and then one of them I call it the dk/dc. I don't know it, I don't care about it. So, do I know the velocity initial? Do I know the velocity he was moving at to begin with? Yes or no? Do I know the velocity initial? Hint, hint.
The answer is yes, you do know how fast he was going, but only at that specific moment.
Right,
You
well,
don't know how fast he was going before.
right, so
You
I
don't
know
know
the
how
velocity
fast he was
initial.
going.
What about the acceleration? Do I know the acceleration? So this is check. What about acceleration?
We might know the acceleration.
Yeah, it's right here.
We might.
No, it's right here. They told us it.
Oh.
Check. Okay? Do I know the time it takes?
It goes in seconds squared. Oh, is that actually seconds squared? I can't tell.
Yeah, that's a second
Resolution's
squared.
bit
But do I
low.
know how long it took him to stop?
No,
No, I don't. So that could be what I'm looking for. Is that what I'm looking for? Because I asked you, how far did he go? That's not what I'm looking for. What I'm looking for is delta x. I put a little question mark by that one. This shows me, hey, I need to figure out what that is. Does that make sense to you?
Yep, makes a
The
lot
last
more
part is-
sense. At least now.
The V final. Do you know, did I tell you anything about the V final?
You told. Well, I can already tell it's the final velocity. I don't need to know that.
Alright, but what is it? What is the final velocity? I didn't give you a number. I didn't write it up on the board. But I can tell you that I know what it is. In fact, would you like to know what it is? I can tell it to you right now.
It's the speed that he's going right as he's about to hit the deer, right as he slams on the brake so he doesn't hit it.
Right, right. But at the end of this journey, his final velocity should equal what?
0?
Should equal 0. Why?
Yes!
Because he stopped.
So he doesn't hit the deer. If
Because
it's
he
0,
didn't hit
he
the deer.
isn't moving.
Right, right. If it were some number, then he would have hit the deer. If he finally stops, then it would be 0. So technically, even though I didn't specifically tell you that the final velocity was 0, you guys should be able to kind of deduce that. So yes, I'm given 3 different things. I'm looking for this one. This time right here is my dk/dc. That stands for I don't know it, I don't care about it. You guys got it?
Yep,
All right, now
loud and clear.
here's how you solve this problem. Okay, look at the 4 equations. You'll notice that of the 5 different variables, each of these 4 equations only has 4 of those variables. So this one doesn't have a delta x in it. You guys see that? The third one, that doesn't have a v final in it. The second one doesn't have an acceleration in it. The fourth one doesn't have a time in it. Which equation do you think I should use to solve this problem? Keep in mind that I don't know, nor do I care anything about time. I'll repeat my question. Do I use the first, second, third, or fourth equation if I don't know anything about time? If you don't know, say I don't know, and I'll tell you. Because I want to get through this problem.
Alright, Mr. Delta, you got me. I'm stumped. What's the answer?
It's the fourth equation. Because if you don't know or don't care anything about time, then use the equation that doesn't have time in it. Does that make sense?
To find out what time is.
Well, no,
Okay.
you don't know what time is. You don't care what time is. You're not looking for it. You're not trying to figure it out. So don't use it. Fair? Don't use the equation. Like, why would I use this first equation if it has t as a variable in it? I don't know anything about time. I don't care about looking for time. So why would I use the first equation? Or the second, or the third, because all of those has a t in it. I'm going to use the equation that doesn't have a t in it. So let me write that down. Here's the fourth equation. V final squared equals V initial squared plus 2a delta x. I'm going to just do some algebra real quick. All right? V final squared is 0. I want to get delta x. I'm going to figure out what delta x is. I'm going to figure it out in just a second. I'm going to pull this guy over, and I got negative V naught squared equals 2a delta x.
Alright.
Then I'm going to divide through by 2a, and so I get delta x equals negative V naught squared over 2a. Now keep in mind that this isn't negative V naught squared. This is negative times V naught squared.
Okay, so we're not calculating a negative direction. That would mean we were going backwards.
Well, no. There still is that negative up here. But look, what will...
Well, I said the negative didn't pertain to the direction, is what I was saying.
Well, yeah, but this negative is still here. So, I mean, your
Okay.
answer, delta x, is still going to be a negative number, unless, of course, a is a negative number, which is nice because a is a negative number over here. So those negatives cancel, which means you were still moving forward. Does that make sense? So all I got to do is plug in the numbers now, and I have delta x is equal to negative 11.4 meters per second squared divided by 2 times negative 3.8 meters per second squared. This negative will cancel out with that negative. Do me a favor, does anyone have a calculator on them? Figure out what 11.4 squared is, then divide that by 2 and divide that by 3.8. Tell me what your answer is.
Repeat your question? Hold on, I have my calculator open.
Actually, I'll just tell you the answer. I calculated it out already. It's 17.1.
Okay.
So did he miss or hit the deer? Keep in mind the deer was 20 meters away from him to begin with.
He missed it, but just barely.
He missed it and he had 3 meters to spare. Cool?
Yeah, so about 6.5 feet. Got it.
Alright. Catherine, do you know how to take a screenshot of this thing, of this slide? Because I'm going to erase this.
Specifically, if you want to take a screenshot of a part of a window, use Nimbus screenshot on the Chrome App Store. But if you want to take a screenshot of the entire window, entire screen, you press Control plus Window switch, the button above the 6 key on your Chromebook.
Well, actually, you can take a picture of just this section of your screen if you hold down Control and Shift window switch. That will give you a little cursor.
Oh my God, this building. Thank you. Hold on, I'm doing that right now.
Alright, I'm going to erase, so make sure you take a picture real quick. Tell me when you're ready.
Okay. Alright, thank you, I got it. I'm gonna go paste it into an email.
Catherine, can I erase this? Okay, cool. All right. The second question is this.
Oh,
Part
no.
B of that
No,
same. Part B of
he
that
didn't
same.
copy.
Well, I have it archived, so you can watch archive. Part B of that same problem is saying, okay, well, how long did it take? So, how long did it take for him to stop? Well, okay, fine. I want to use the one that has. I want to figure out what t is, so that's my question mark now. Okay. Do I know my velocity initial? Yes or no?
Yes, we do.
Do I know my
We do know
acceleration?
how fast. We do know We do know acceleration.
Do I know velocity final?
You do not. That's why That's what we're calculating it for. So we need to rewrite the equation so we can calculate that.
Nope, nope. I totally do know it. Catherine, what's
You
the velocity
do?
final?
Let's-
I'm applying the same scenario.
I'm
I'm just
sorry.
asking how long does it take for me to stop. So what is my v final? It's 0. Because I stopped. Do I know delta x? Now technically from part A, yes, you do know what delta x is. It's 17.1. Why? Because we calculated it out. However, I would argue with you that for part B, don't use 17.1 meters for part X. I would say that this is your don't know, don't care. The reason why I would do that is because even though we do know it, what if we screwed up on part A? That would make part B wrong. So
Wait, Mr. Dalday.
let's use a quantity that we didn't calculate, and all of these were just given. This is what we're looking for. Justin, what's your question? I only got a couple minutes to answer it.
I was asking what's this question from? Is this for the quiz that we're taking today?
No, this is actually straight
Yes.
This is straight from the textbook. It's on page 36 of your textbook. This example is worked out for you. But I want to do a bunch of examples for you.
Okay. Hold on, I'm going down to page 38.
And by the way, on Friday, I'd like to do a WebEx, or I'd like to do another lab with you guys. I should send out an email soon.
Okay, on Friday, hold on, I'm going to go record that.
Alright, anyway, which equation now should I use? I've got V final, V initial, A, and T is what I'm looking for. I don't know anything, nor do I care about delta X. Which one of these 1, 2, 3, or 4 equations should I use? Catherine, you still there? If you don't know, just say I don't know because I'm running out of time. Do I use the first, second, third, or fourth equation? Okay. Catherine, what you're going to do is you're going to take a look at what you have. You have the V initial, you have the acceleration, you have the velocity final, and you're looking for the time. That means you're looking for one of these 4 equations that doesn't have a delta x in it. Only one of those is the first one. The first one has no delta x in it. See, this is a delta x right here, this is a delta x, and this is a delta x. So I'm going to use that first equation, and I'm going to just write it down. It's V final equals V initial plus AT. And they want me to figure out what the time is, so all I got to do is solve for the time. All right, fine. I'm going to take this, move it over there. I've got V final minus V initial equals AT. I'm just going to divide by A, and so I have T equals V final minus V initial, all divided by A. You plug those numbers into your calculator, boom, you're good. The answer is, well, this is 0, and this is negative 11.4, yeah, meters per second, and this acceleration is negative 3.8 meters per second squared.
Whoa.
So therefore, that would give me 3. And how do the units go? It would be 3 seconds because, see, this meters cancels out with that meters. This seconds cancels out with one of these seconds. So I'm left with 1 over seconds, which is also known as seconds. I think that I might have just blown your mind. I'm going to let you take a picture of it so you can kind of mull over that. You have any questions? All right. Take a picture of this. Have fun. I'm going to stop the archive.